session here for the last day of FTP. So I once again welcome you all in the second technical session of this fifth day online FTP on system engineering, sponsored by AICT Atal Academy here. So let me start with the presentation. Then so a very good afternoon to one and all present here. I, Dr. Sierpinski Tripathi, is here to present the topic IoT and variable antennas here. So before we move on here, let us see, because when we talk about the antennas here, the antenna is a transducer which converts the energy from one form to the another here, from unguided to the guided waves, yeah, or guided to unguided, so vice versa here. So this is the way antenna used to function, provide the communication between the wireless mode here, from source to the receiver here. So when you talk about the radiation mechanism of the antennas here, so for the radiation, it need to be a time varying current, acceleration, deceleration of charges here, or if the charge is not moving here with uniform velocity here, then here either need to be curved, bend, or discontinuities here, or this will be truncation in order to enhance the radiation, which will lead to the final enhancement of the radiation part here. So if the charge is oscillating in a time domain here, then we would always have the presence of the electromagnetic waves here. So time varying electric field will lead to the magnetic field, and time varying magnetic field leads to the electric field here. Antennas here with respect to the one with other here. So let us move with respect to our topic of the wearable technologies here, and then we'll try to explore what are the IoTs related activities here. So how the IoTs fit in the case of wearable technologies here. So let me clarify you this is here. When you talk about the wearable technology here, so a lot of sensors are already embedded or part of this kind. So once a lot of sensors integrated with each other here, so they could be connected to the wired with respect to each other. Then there will be one mode from where they will be communicating with the outer mode here, or the nodal center here. So when we talk about the wearable technologies here, so there are these are the few of the glimpses of wearable technologies in the present form here, where how these are the shaping of in the coming futures, or the way it will be leading in the uh, uh, so in the first you can see there is a embedded chip in the inside here they have put here. So these are the threads, uh, in the lining here. You can see these threads will be working as a conducting medium for the communication. As well as you can see the other few designs they have deployed with these threads. People are trying to explore it, some kinds of conducting medium here, because the objective is when you are trying to place the antennas here, or near to the body here, so you need to be extra cautious compared to the previous cases of our design here. But once you put it in very close to the human body here, at that time you have to consider the SAR values as well as the losses associated with the antennas here. So we'll come to the part little while here. So these cases you can see there is the last two. You can see there are some chip or some PCB we have already fabricated. We are placing it, some additional circuitry, some sensors unit. We are also integrating it here. When I'm trying to put it here, this is the open bag here. So within the bag, a lot of sensor unit with the PCB part is integrated, and we are placing it here. This is a fabric part. You can see this PCB is connectivity is through these threads here, so they will be providing a medium for the communication of information here. So these sensors will be collecting the data and they will be communicated further through these threads here. So if you see the kind of variable technology here, and if we see the global perspective, its impact here. So it is very well articulated by the key, variable technology markets experts here in 2015 here, that the variable electronic business powers from $20 billion in 2015 to almost $70 billion in 2025 here. So now you can see a significant jump of more than uh, 3.5 times here within a span of just 10 years here. So you can see at least 5 years, it will be 2 times years. It will be already happened here from 20 billion to the $40 billion. It will be approximately going on at this time of time here. So here, so what are the things which are managing or the facilitating for such kinds of technology? So much growth here, which will be based on the few of the recent progress. If you try to look here, then if you see the conductive threads, this is the one point, because when we need to design an antenna system here, at that time we need to provide a feed, or means some way we need to provide the make sure that power will reach to the antenna system here. Because at this stage, generally, for the power transmission, I need to provide a connecting wire systems here. So when you talk about the variable technologies here, it is not feasible here to use those conventional kind of wire here. Because in conventional wire here, there's a highly likely chances they make get the fire here, or due to the heat up issue, they will be melted here. So if you are placing some kind of circuitry which is sensitive to, which is close to the body here, then you need to be extra sensitive when you are dealing these kinds of applications here. So these extra sensitivity as well as the security of the persons when whose proximity here we are placing these kinds of structures here. So generally, this is conductive threads as well as the advancement in the RFID tags here, as well as the near field communication technologies here, has contributed a lot in the overall growth of the variable technologies here. So when you talk about the variable technology here, this is a subset of wireless body array network part here. In the body network part here, there are three aspects people are exploring this body array network part here. So first aspect is body network part, or variable technology, is the off body array network. So off body array network means what is the device we are thinking to collect the information related to the person here. It need to be a place will be far away from the your human body here. This will be the off body array network here. Then comes to the on body array network. So on body array network, so device will be on your body here, and the device is on the body here. So what are the power you are providing to the device here? You need to be very alert. Well, what are the power will provide here? So those powers may be absorbed by the our human body here, because the human bodies have the OH minus ions here, and they are very sensitive for in terms of absorbing those electromagnetic powers here. So it will may happen when you are giving the power here for the transmission purpose here, but it may happen that those powers have been absorbed by the system, it's by the human body itself here. When the power is absorbed here, it may cause the heat up, itching, or a lot of new kinds of disease or undesired effect will be observable here. So it is advisable here to not to you advisable to be very careful when you're going for the on-body communications here. And then the another kind of category here is the in-body communication here, in W band here, or means these kinds of application comes with the implantable body array network here. So the devices will be placed inside your body here. So in this kind, this is the utmost sensitive part here. You need to be utmost sensitive in such kinds of appliances here. And when you are putting on for the gathering the data inside the body here, then you need you need to ensure that devices are working at very low power level so that they will not be having any health effects on the human body here due to their associated power level. At the same time, the moment you say the power level comes drastically to the very low level in the terms of microwatt here. You cannot transmit the power in the more than order of microwatt by placing a device on the body or in the body here. So even a smaller power level you used here. Here, when you go for the these kinds of devices applications here. So when you talk about the wearable technologies here, we are generally more concerned about the second category, on-body wireless body area network, where the some devices will be around surrounding your body here through the uh, your daily VS here will be managing to place somewhere near the body here, or you can throw some electronic gadgets here. We will be putting it some different location of our body here and trying to get different informations here. So this is the one of the evolution history of the wearable technologies here, which is shown here. So when they started this variable kinds of phenomena then starting here, and then the people started first through this ring here, so they were placing this ring here for some information here. So then from there I was considering the gambling shoe, the digital hearing aid, then Bluetooth headphone, Fitbits here, then smart watches here, then the Nike fuel band, then the Galaxy Wear, then subsequent Google Glasses, then Google Watch, Google Fit, Apple Watch. So this journey is keep on going here. So when you talk about the history of wearables technology here, so it is present here in some of the different sort of form here to gather some kinds of information related to our human body here, and then they were trying to catch those information, don't directly, or you can say. By putting some specific test here, but some other form through the help of some sensors or some embedded devices here, we could collect those desired information here. So when I say the why this variable is so important here, and why the people are talking a lot of related to the variable technology, or why this much buzz is happening here. And the nowadays it is coming here, but if you see from the application perspective as well, the what kinds of benefit I am getting here with through the variable technologies here. So you can say they are continuously present with our surrounding here. So one way they are providing additional layer of security to our human body by observing our body's behavior here, and they keep on monitoring here. You can say one doctor, or you can say in some sense, doctor consultation is already available to us here in a very primary form here with us. They are keep on monitoring our database here. They are keep on tracking the record of our body movements here. So the moment they will observe any abnormality here, so it will be known to us within a very little span of time here. Also immediately it will be known to us here. But otherwise, if you see it, if you're not wearing these kind of devices, you don't have information, then if I feel some problem here, then I have to go for the regular checkup to the visit to the hospitals here. Then I need to go through certain diagnosis here. Then I could say, okay, fine. These are the problems here coming, and based on that, these are the outcomes here. So I need to take the precautions here. But what if these kinds of measurement are taken place automatically by placing some device near to surrounding here, which is obviously is not harming to our body here? Then we can think of such kinds of devices in our surrounding, which will facilitate us in our life. So these kinds of devices is becoming feasible nowadays here because some of the latest advancement here in terms of the fabrics here was a biggest challenge when people thought about the such kinds of wearable technologies. is how you can provide the power. Yeah. Because designing and other things is the one aspect here, as well as the safety. Safety of the body is another aspect here, but the crucial from the point from the implementation perspective was how would you provide the power to them here, because these devices will work only when you provide them power here. Yeah, so the advancements in the threads here, which will have some kinds of conductivity phenomena here, will not go to the material properties of the fabrics here. Here, so here any or you can say some kinds of yarn here, or some conductive yarn here, which will provide some kind of way to facilitate the facilitate or provide a medium for the conduction of voltage. Or someone is facing problem in connectivity, so one message has pop up here regarding the connectivity. So am I connected with a major chunk of you, or it seems I'm connected side here, that's why you're disconnected here. You need to check it here, correct? So let's back to our discussion here. So there are some other materials which will be also used here to explore this wearable technology part here. So one is DuPont's stretchable here. Mhm. So where this your antenna, as well as the other circuitry will be placed here on this device itself here, or it's the fabric flexible substrate. This will be printed and this will be working as a mode of conductivity here. So nowadays, a promising area is related to inkjet printed antennas here. So some kinds of inks has been already prepared here based on the silver, gold, and platinum compositions here. So if you go with the printing of those kinds of ink here, so this printed ink will have some conductivity phenomena among their cells here. So this printing will work perfectly just like your normal antenna system here. But if you compare with our PCB design as well as such kinds of inkjet printed design here, you will see in terms of their dimensions here. Because whatever the characteristic of phenomena you're observing within a compact dimension of PCB or copper plated PCB here, if you look to explore a similar kinds of phenomena here from a printed device or material here, then you need a larger area relatively here compared to the PCBs here in order to get those kinds of characteristic here. But yes, the answer is yes. With these kinds of fabrication on the flexible substrate, we could get desired antennas characteristic here. And our core service providers, Intel is also not behind in these kinds of contribution here. They have also provided a flexible chip here, like Intel's Curie here. So they could be also integrated with our variable requirements here in order to fulfill the computational requirement part here. So from all the ends here, this you can say innovation is going on here. So collectively, we will be in a position here to have a better lifespan. So the other solutions have which can be proposed within a compact direction is the C series solutions here. Within the C series solutions, it will be a variable or near so their fabric have been placed here, just like a button. Have you seen in the initial slides here? This one here. You can see few of the design part here is present here. So this is the further exploration part at this side here. So within this, each one of this C series section here, it will be equipped with the different kinds of sensors like temperature, pressure, gyro management, accelerometer, light sensors. So these kinds of sensors will be present here. They will be keep on tracking on these parameters continuously near to our body here. The moment we started to walk here, they will keep on observing. The moment we started to and go for running here, there will be change in the pressure, temperature here. So these things could be observed by these sensors here, and they will be keep on reporting here. So these facilities could be present here within very small unit here. But the important is in such kinds of units how we are going to manage their power consumption here. As they are present, so you cannot directly feed them with the power source directly here. So some forms of the battery devices which you are using here, they need to be very sensitive in terms of their power consumption, so that you will have a longer span of time here for the operation purpose here. This is one challenge here people are facing in case of wearable technology here. When you talk about the IoT's antennas here, so IoT is just a medium here for the internet working of physical and virtual devices here for collection and transfer of data here. So in case of wearable technology, a lot of devices will be connected here and near to our body here. So the objective is to cache those data here and then further to transmit here. And so when you talk about the I2 antenna technology specific here, so the antenna is the one component of this overall solution system here, where it provide freedom from the wires here. So without uh, the restriction of one place, I can move to the different locations here. I have the freedom to move, go different places here, and still I will be in a position to the communicate the information continuously here. So these are the few examples I have listed further here in terms related to the wearable antennas here. So the previous we talked about the antennas technology here as well as the wearable technology earlier here. Now we are coming precisely to the wearable antenna technology, which we are trying to understand. So wearable antennas are essentially an antenna that is specifically designed to function while being worn here. So whenever we are going to use some kinds of electronic gadgets here. So obviously they will be present near to our body here. For example, if I talk about smartwatches, it need to be placed to the our near to the body part here. A smart glass here. Still, it will be close to our human body in here. Or if I'm going to put some sensors here, which is part of our jacket here, or our any other places. If I'm going to put a suit tracker or other things here, if I am trying to include here in the list here. The point is, when you're going to use such kinds of devices, first they will be very close to our body, and second, the antenna functionality should not be altered or the hampered here when I'm going to place them near to our body here. So this is the important consideration related to the these kinds of wearable antennas that I'm trying to design it here. So either we talk about the smartwatches here or the glasses here. If you talk about the glasses here, Google glasses, and then they will be collecting the information, and they have the mechanism to transfer this information to the Wi-Fi module or the GPS antennas here to the base station here. I could always have the liberty to see it here. So many spy movies you have seen. Some person is wearing a glass here, and whatever he is able to see here, the rest could be displayed to the communicated to the base station here, and there you people can observe through the eyes of that person what is happening at that particular place here. So. Due to the advancement in the consumer electronics here, these kinds of application or the market is increasing significantly, and the people's interest is also increased significantly in the coming years here. And, so when you see with the electrical characterization of wearable substrate here, because whatever you are dealing here or trying to achieve here, so a lot of part is generally governed by this electrical characterization of variable substrate. What kind of substrate or from where I used to take the inspiration for the design here, it will be mainly based on the substrate part here. So as we talk about the variable antennas here, so variable antennas they generally can be used here for the medical purpose as well as non-medical applications here. They will be operating in the several frequency range and build on various substrate here. So based on their range of frequency, there will be power constraint will be one aspect here. So for the development of variable antennas and other electromagnetic variable devices, it is crucial to know the electric characteristic of the flexible substrate used here. So to characterize or you to know the substrate material behavior here, there are different methods have been proposed by researchers here, like coaxial probe, transmission line, free space, resonant cavities, and parallel plates, etc., etc. Here. So based on either of them, I can use it to characterize the substrate behavior here. Among them, coaxial probe is very easy. You simply need a two probe here to put the two places here and find out a lot of information related to the behavior or against substrate which I am trying to use here. On that substrate, I am trying to design any antennas here on circuitry for the variable part here. So complex dielectric permittivity as well as the loss tangent permeability, all this information could be measured very easily here. So once you have the information, you could get an idea okay, how it is non-destructive, it is broadband, narrow band, what is the temperature related sensitivity of this material here. All this information could be observed through the coaxial probe here. So with this, it is easy and a lot of general information which we needed here could be available with us here. So we go through the coaxial probe very frequently here. This is the one textile patch antennas here, which I am considering here, just for our understanding here. So when we are trying to go for the variable antennas here. So textile patch antenna is one aspect and the PCP antenna is another aspect here. So both of antennas are used here in the design of textile variable antennas here. So one antennas when you are going to design the antennas here for this variable part here, then people based on the application sometimes design directions here or the mostly it is desired here for go for the omnidirections here. Antennas, if you design the antennas here where antenna's location is fixed here and it need to communicate to the other station. For example, if I need to place some sensors here and all the sensors will be integrated will be connected with through our mobile phones here. For all such kinds of application, I need a very low amount of power here, which can be given to those sensors here for the transmission with the antenna system, because further communication process will be taken care by the antenna. Their task is what the information is collected here, they need to be transferred to the antenna system here. So based on that, we need to design the antennas here. Or in general, if it is circular polarized here, that it is better here. And at the same time, when you're putting the antennas here, so that beam of their radiation should be coming outwards here, always towards the outwards of the body here. It never goes to the towards the body here. Otherwise, it will heat up the our body here. So this is the one example here we are considering, and there's a variable technology here. So there are two kinds of antennas have been placed in this design flow here. So one you can see there one is used as a textile antenna, just discussed previously. Another he has used a PCP antennas here to gather the information here. Correct. So compared to the these two antennas, if you see, both have their possibility to be deployed on the body part here, but it need to be application oriented here. So if I need to put something at the our shoulder part here, then obviously it need to be some kinds of flexibility because that cannot happen. But if something is coming over backside or a chest side here, then if it is a PCB here, it will work fine here. As we all know that when you are going for the PCB design here, if you go to the literature here, you will observe those kinds of solutions discussed by the researchers here. So, in summary, we have discussed few things here, but let us summarize the challenges part here related to the variable antennas when we are trying to explore here. The first and the biggest problem is related to the proximity to the human bodies here, as we are putting the antennas near to the body. Whatever the antennas in general, it will be performing here, but the moment you put it, it it affects the radiation behavior of the antenna significantly here. So this is just a stats here to emphasize how adversely it could affect the presence of body to their antenna performances here. That if you design an antenna and measure an efficiency of minus 3 dB, when we say the minus 3 dB means 50% power is lost here, 50% power is available here. And place on the body, the efficiency may easily drop to the minus 13 dB. So from 50%, it will further drop to the 1/10 here as a 5%. How drastically your body could impact the antenna's behavior if you're not designing it properly, considering this aspect in the design here. At the same time, very limited volumes here, so variable devices must be as small as possible. So when you are looking to for a very compact dimensions here, and then a compactness is generally explored through the PCB approach of the design here. To the PCB path, we can always design. As we have seen, we have the now the conducting threads available with us here. So the connecting threads here, I could connect them with them here, and I will have the mechanism to excite those structures here. Here. So now we have the chances to infuse these kinds of PCB devices for our variable purpose here with the advancement of conducting threads here. So because they provide the compactness in the design here. So the one example which pop up here, or the design which is mainly governed here in case of variable antennas part here, it is people have thought, can we design something which will be robust here, or you can say whose behavior will be more reliable as well as predictable here when you are going to substitute it here or place it here near to the body. What kind of design will be appropriate here in such kinds of body applications here for the bio-inspired? So the people has a thought as a solution. Why can't we take the inspiration from the surrounding, or you can say nature here? So we thought, because if we see our plants as nearby to us here, if we see they have been optimized by the nature itself here. Based on the different objects, if we see here, everyone is optimized based on its characteristic here, and to go for the proper processing here. Because we all know that there should be every plant will go for a photosynthesis process here. So when you say the photosynthesis process here, means there is some energy or sun rays that is falling to the falling on the plant's leaf here, and those leaves are efficient here enough with respect to that plant here, efficient enough to convert, to go for the photosynthesis process and convert that energy against to the chemical energy for their utilization here. So in this process, if we see the very qualitative way, some kinds of energies has been fall to those plants leaf here, and these energies further is converted to the some another form of energy here. When you look from the antenna perspective or functioning here, what we are looking, so at the receiver end, some form of electromagnetic wave is fall on the antenna system, and this energy is converted to the electrical signal, voltage or current here. So in terms of functioning, there is a direct, there is an analogy between the functioning of a plant leaves here, or functioning of plants in behavior here, similar in the nature, just like the antenna system which is working here. So now if we correlated this property here in the design of our antenna system here, then a lot of advantage we can get here. So based on this inspiration of bios, or you can say nature here, or you can also take nature inspired variable antennas here for the optimum performance as well as the optimum results here in case of a body and network communication here. So the reason is because the nature already optimized those structures here with respect to that here. So if we can use those optimization or iteration property which the nature has already done here, which is given as a final shape to us here after considering all the optimizations here. If we use them directly in the design here, then how can we get will be how it could be advantageous to us here, correct? So the one advantage which will comes to us here when I'm going to use this kind of structure is that the compactness in the design will be achieved very easily through the this kinds of bio-inspired antennas here. So how this compactness is coming, we will see a little bit later here. So once the compactness is coming here, as well as they will provide the electrical length more here, there will be some fractals, or you can say there could be some bendings, there will be the curves in the leaves here. We discussed earlier here. This is the fundamental laws here. If there is a bends, curves here, or discontinuities here, then all those cases here, it will lead to the enhancement in the radiation here due to the change in the current path here. Very much aware these things here. So, based on these years, how we can utilize the people have moved for a solutions here, which is known as a fractal geometry implementation in the antenna design here. Correct. So these designs, when you say the inclusion of the fractal geometry in the design, it is totally based on the bio-inspired or nature-inspired design inspiration we have taken here in the design aspects here, and we are trying to include it in the antenna design perspective for the enhancement in the radiation characteristic here. Okay. So when you look these objectives here in the nature, it's original safe here. So you can see some of the popular factors nature here available here. So people have observed that when you go for the nature here, there are some self similarity here. Even if you see any trees here, so there was a leaf. If you see the similar kinds of leaf will be available here, very large in number here. If you see the cactus here, similar kind of structures will be keep on repeating here. If a plant here, any a leaf of any plant, if you see similar structures here will be so you can see it will be just the scaling of that one ideal design here. Whatever design is present here in the leaf here, it will be just as scalable. Someone will be larger, someone will be compact here. So the people have thought, why can't we use these kinds of phenomena in the design itself here? Right. So as we can see, these objects look very beautiful here. If you have to observe it here, but if you think, if you have to design such kinds of complex structure in the simulator here, so the how complex your life would be here. Here, if you want to design just exactly the replica of this kind of structures here, how many years you are going to spend it to design it here, right? As well as do you have the from the fabrication perspective, do you have the accuracy to go for the exact fabrication at such a manner here, such kinds of 3D printing of the PCB design here, right? So we need to also make a trade-off whatever is available to us in front of us here, as well as from the our end the available resources and capabilities here, up to what extent we can move on here. So this was a trade-off here. Based on that trade-off, people has come forward to some of the solutions here. So the solution related to the factors we discussed, but prior to that, the objective for utilization of factors in design was to achieve the miniaturization in the design, as well as fractal will lead to the discontinuity in the design, so enhancement in the radiation, as well as it will help us in the proper impedance matching to here. So take less area due to the many contour of the shape here. This keep on discontinuities, and there will be discontinuity will be available at the different scale here. So discontinuity overall help in the overall enhancement in the electrical size of the antenna here, as well as when you similar kind of structure here when you're using here, then in those cases a multiple resonance corresponding to those different scale length will be generated here. Point is, as we have discussed, the electrical length of the antenna is proportional to the wavelength here, and this wavelength is inversely proportional to the 1 upon a frequency here. So whatever the length here we have corresponding to that level, it will have a corresponding one resonant frequency here. So there will be a periodic behavior will be observed here. So higher order harmonics will be present here. So that will be another thing. But still, if I see corresponding structure, if I have a same structure but the different scale here, here. Suppose if I say there is a something like this here. All of these are the here pen caps here. If I say this is the pencil here, if I can make it half of this level here, I can further enhance it to the double of this level here. So in that case, you will see based on the dimension of the antenna here, it will have the corresponding resonant frequencies here. So whenever you're going for these kinds of fractals in nature here, so due to the presence of self-similar structures here, replication in the overall design, they will have the multiple resonances presence here in the design. And the overall multiple resonances, overall effect is observed here with the fractal designs give us a wideband kind of phenomena here. And wideband kind of phenomena is very much desirable here. So few of the popular fractal models which are used in the design is Coase model, Sierpinski model, as well as the Minkowski model here. So these are the ways to how they will go from one iteration to the another iteration here. So here you can see this is from antennas here. First iteration is like this. Second iteration, each one is broken again in the same similar manner here. So each segment of this arm is going to be replicated in the course form here. So if you go for the further iterations here, we can see if you go for the higher order of iterations here, there will not be a significant change in terms of enhancement of the dimension as it is observed here, as well as complexity is also increases significantly here. So people think here, if we cannot fabricate those level of accuracy here, here, then there's no point of going to the higher order iteration and to increase the complexity of the structure here if it is not reflected, as well as based on the performance of those structure it is observed here that initial few iterations is only beneficial. If you go for the further higher order, there should not be any much significant change in the overall performance of the system here. So, this is the Sierpinski triangle construction here. So the triangle initial, the first iteration there will be one triangle out of this one here, another triangle. So this model will larger scale is generally called as a generator here. So we have taken the generation here. So this is a triangle initiator. This is a coach geometries here which you are considering. This is generation here. So after that, once you apply it, so you will get the coach curve here. So each arm of this triangle here, or each segment of this triangle will be you go for the iteration here. So you can observe this kind of behavior, or you can say coach curve here will be observed here after the first iteration of coach curve here. If you go for higher order, there will be this self-similar properties will be keep on replicating at the different scale here. So now, if we see these kinds of structures here, then people have thought here, as we are talking about the variable technologies here, so the variable technologies nowadays with the advancement of mobile phones here, it is notice here a lot of devices, sensor integration unit could also be connected with you mobile phones here. So high power to the near to the body here, can we go ahead with some alternative solution where we can reduce the power level here? Right. So how we can reduce the power level? If you remember the channels, Sennon's law here, C is equal to channel is equal to. Mhm. If you see that link here, you can see there will be channel capacity is equal to B into log 1 plus SNR here. If you change the bandwidth here, then I can also increase the channel capacity. Either I could go for the SNR, but here when you get a body network, SNR is directly proportional to the power level here. Here, so I don't have the liberty to go for the higher power. I cannot go for it. Either I can go for the antenna array or the MIMO concepts here, so the UWB here. But MIMO concepts here, there's a answer is yes, we can go for it, but a very low power level here. If you go for the MIMO here, the advancement will not be so significant to fulfill our requirement here. School has thought for another technology or the solution here, which is generally called as a UWB ultra wideband technology, which will be see a little bit later. So let us see this first example here, then we'll move on. So here in this case, based on the inspiration of the variable antennas here, so one has taken the inspiration from the Jasmine flower shape here. On the Jasmine flower shape, they have proposed antenna design here based on the design antenna. And they are observing good, you can say, ultra wideband behavior here for the operation purpose here. So as we have discussed, this so here you can observe when you design this kind of structure here on the flexible substrate here. So when you are going with the flexible substrate here, so even the small bending and other things will be very common phenomena with respect to the overall antenna system here. So here you can see when I'm wearing something here, so based on my movement here or my activities, it is highly likely that those kinds of structure will go for the different deformation here. So based on those deformation, what the changes will be reflected in the overall antenna's behavior here, it need to be noted down properly here. Correct. So if we are going to look at the behavior of these systems here, so based on the forward bending or the backward bending of the antenna structure here, you can see their original radiation behavior, I was S parameter behavior is changing significantly with respect to the bending as well as the forwarding activities here. So here you can say some part which was in the operating range in the initial design here, now it is not part of the operating range here. So and the people have thought from here how when we are going for the near to the body here, so this is affecting a lot to our body part here. So how we can move ahead to the further here, so that we can deploy these properties here. So the solution they have proposed is a UWB technology here. When you talk about the UWB technology here, then it operates from 3.1 to 10.6 gigahertz. That is operating in such a wider band here, and the overall bandwidth available to us is 7.5 gigahertz. So such a wide bandwidth, we have the liberty to get a very good channel capacity here. So when we will get a very good channel capacity here. At that time, if I look from the conventional narrowband applications, narrowband band is small, as well as the power level is also confined here. So we can't move ahead even with the application we want also. But if we see it from the wideband UWB technology, now I enhance the bandwidth. So the moment I enhance the bandwidth here, I can accommodate more number of IoT services here for the transmission of their information here. And the beauty is, even when I place those structure near to the body here, even if some section, some part of the operating band is deformed here, it will be some aspect, there will be some form, it will be affecting to us here. So here, so it may affect partially or slightly here, it may affect the drastically here based on the design, what we are designing here. If in the design initial part you consider these aspects here, then you can minimize this effect aspects here. But if it is not here, then it may affect it drastically. Overall performance could be completely destroyed here based on the body network effect here. So once they are going for this kind of thing, even some part will be not working properly here after the body effect, but still there will be significant band will be available to us here for the transmission of data. Second, when you are going for the use with the low power here, so the low power here, as they need not to go for the very long distance communication. Their main objective is to go for the communication from the sensor node to the nearby mobile phone or nearby the node sensor when they need to communicate here. Their objective is not to go for the complete base station which is 100 or 2 kilometers away here. They need to communicate to the nearby mobile phones. From the mobile phones, it will connect to the gateway here. Or they need to communicate to the node here. The node will take care of the further processing of that information. So there is a small range of communication which will be need to be targeted by this UWB technology here. So when I'm going for this UWB here, we are getting the biggest advantage. I need to keep my power level low. If I am able to keep my power level low here, I am getting a lot of advantage in terms of related to the body related hazardous effect here. If the power level is low, so the absorption by the body molecules of the electromagnetic waves chances have been reduced significantly here. If it is reduced here, so those hazardous effect chances have been also reduced significantly here. So this wave could minimize the overall impact here by moving ahead. But the people have thought if we go for such kinds of complex structure, if we see structure here, so in case of these structure here, when I'm looking for the fractal geometry implication here, as we have discussed this one here, if I'm looking for such kinds of fractal inspired structure, self-similar here, where such kinds of structure could be repeated here in the design itself here, how we can move on. So if someone asks me to design a triangle in the simulator, I can design it. Even if you go for the first order iteration, I can design it. But what if someone asks me, you have to go for the further, this is the initiator, this is the first order here. If someone asks a second order iteration, third order iteration, and so on here. So designing those things in the simulator here will be very tedious task here. People have thought what could be a more systematic way to approach this problem here, and we will get so that we can get the inherited by the benefit of this fractal geometry, but at the same times we not should be affected significantly through the complexity of such kinds of fractal structure in the design here. Yeah, so the solution it comes as a iterated function system algorithm here, which help us in designing the fractal geometry here. So you can see W is equal to XY is a matrix form which is 1 by R cos theta minus 1 by R sin theta, 1 by R sin theta into 1 by S cos theta, X and Y here, and these are the axis value, plus E and F here. So R and S is scaling factor in X and Y direction, theta is the rotation angle in the same plane, E and F are the translation in the X axis and Y axis here. Correct. So we are keeping one example of course curve here. So course curve, when I say this is the example I considering this one here. Correct. So if I see with respect to this one here, so first if I take this initial simple line here, so this line has been changed to like this. From one section here you can see I am going for the 3 equal section. So out of that I have break it in 3 equal section. So now from each equal section 1 by third segment length here, I am forming this new dimension here. So here you can say this is the one plane. Here there is no angle, but here you are getting another angle, and here you are getting another angle, and at this stage again this is a flat here. Correct. So this is the one here where we have the zero elevation. This is another way zero elevation, but in these two segments we have the angles present here. So how could we deal with the theta part in this design here? So this is the one example for the coach curve which is given here with respect to those matrix values here. With respect to the each iteration here, each segment of if you see here. So as we are going for the 3 here, so we could take this value. So first part, second part, as we are going for the 3 segments here, so it will be 1 by 3 here. So we could go for it. If we want to go for the higher order, I can change the value from 3 to 4 and 5 and so on here, but I need to see what kind of structure it is also going to present here. And also we are observing that we are going to get a 60-degree elevation. At this stage, we are getting this angle as a 60-degree here. So so now this is coming 1 by 3 cos 60. Previous case, W0 iteration, when it was a straight line here. So when I say, when it is like this, sorry, yes. So if you see, this is a W naught is this one here. W1 is this one. W2 is this segment. W3 is this segment of the design. Here. Corresponding to all these 3 segments, if you see, the first one, 1 by 3, x-axis, if you see coordinate point, if you see here, so how they are showing the variations here. So these are just find out, so the 1 by r cos theta minus 1 by s sin theta here. So as we are going with the same structure here, same level of scaling here, so r and s values 3, so it will be 1 by 3, 1 by 3, you can observe throughout it is present here, correct? In the first case, there's no angle elevation here, so it is cos 0 here, cos 0 value is 0. Second elevation here, this angle is subsequent to w by 3. What are the coordinates values are varying here. Based on that, we have formulated this iterative matrix corresponding to the cos symmetry here. Once we have formulated this symmetry here, we need to simply put it in this iterative function system algorithm here. We can formulate other values here. So when you're defining the structures here, there are 2 parameters which we need to understand. One is a self-similarity dimension, which we define related to co-symmetry here. This is a log n divided by the log r here. So log n is related to how many segments we are using here in the design. So if you remember, in this design like this, we are using the total 4 segments: 1, 2, 3, 4. This n value is 4. In case of r value, it is I have divided the it is log 3. It is 1.26 here. So you can say whatever the length was initially, it is going to be enhanced by the 0.26% here in the next iteration here. So if I keep on increasing the higher order here, so this way this length will be keep on increasing in this number. So the total length of a curve is given by L is equal to h and by r here. So you can say in the present case it will be 4 by 3. Right? The first case it will be 4 by 3, but the second case, if you see the second iteration, it will be 16 by 9. Correct? If you see 16 by 9 here, then there will be another. If you go for it, will be 64 by 27 here. So this way, this number will be keep on increasing one after another iteration here. So if we keep on increasing the iteration, the overall effective length will be keep on increasing here, but it will not go to the infinite. Finally, it will be tending to the L here. So this L value, if I go for the iteration, when the n will be tending to the infinite here, at that time it will be equivalent to the initial length L here. So total maximum length you can obtain will be equal to the 2L here. So this is the generally a way we can design here in the simulation software. So I'm going this flow chart with the HFSS here. So using the fractal geometry, using this iterated function system algorithm, I can design this kinds of fractal geometries here. Once you have geometries, you want design here. Now you can the Visual Basic script file here through Visual Basic script file. You could import that MATLAB file into the HFSS here. Whatever the design you have generated here, you could now replicate it in the HFSS simulation software. It will be available here. So design a patch antenna using imported fractal geometry. You can design. Now based on that, you could test what is the UWB performance. It is okay or not here. Based on that, if it's okay, stop. Go for the fabrication and testing part here. If it is not, go for the iteration of some design parameter here. You can go straight. So here this UWB technology here, you can see digital data here you can observe. So what I'm trying to emphasize here, when you talk about the UWB technology, so with respect to the other here, if you see the power level, it is minus 41 dBm per megahertz. It is a 500 microwatt level of power we are using here. If you see relatively the power level of other technology here, we are going with a very high power level here. So with respect to the body and network part here, if I look here, then UWB technology will be a very promising solution here to facilitate the IoT applications here. Because in such kinds of very low power level, I could use it any range of frequency because I'm not interfering with anyone here, anyone is licensed user here. But with respect to the other technology, this amount of power will be considered just like a noise floor here. So at the UWB transmission, whatever the code we are using, PN codes we are using, based on that their orthogonal functionality, I could always differentiate them at the receiver end. So what I have transmitted. So we can differentiate it. It's not an issue here, but it need to be a low range, a very high range. If you transmit here, then the losses will be so significant that we will not receive anything. It will lost here. So in case of UWB, the constraint it need to be a low power, or you can say a small range communication purpose here, not for the very high communication. So based on that UWB, we have discussed this part. Okay. So we are considering one of the problems related to the UWB technology here initially here, and then we'll try to explore here with respect to the IoT also here. As we discussed, the UWB technology is very promising solution provider to us here. And when it comes to the antenna design for the UWB here, then the circular antenna is the ideal one for the design. One can ask why the circular only, why not other shapes here? Because if you have gone through the literature here, you will see thousands types of designs or thousand structures are available here and projected by the designers here. So the beauty of this kind of a structure is, if you see from this point, here, from this point onwards here, you will see this nature of this structure is circular nature is like this. This its curve will keep on changing very slightly. If you what are the point, if you take it here nearby 2 points and point here, there will be a slight change in the curve here. There will be some bending in the design here. And what we have discussed when you're having discussion on the radiation part here, whenever there's a curve, discontinuity or bending is there, it will lead to the enhancement in the radiation here. So if you go for such kind of circular structure here in the nature, then it is highly likely that it will facilitate or enhance the radiations here. If you go through the structure here, so a lot of wideband technology solutions have been proposed with the help of circular kind of shape in the antenna design here. Okay. So this is the surface kind reflected with based on the different frequency band here. At the same time, there is a one more problem here. Here people used to face here. So initial lower frequency will have the standing wave phenomena, but when we move to the higher frequency, we will observe a traveling wave kind of phenomena here. It is observed at the high frequency here. So once we go for the higher frequency here, at that time this traveling wave phenomena will be present here. So once the traveling wave is phenomenon is present here, it will lead to the enhancement of the cross polation as well as the losses too here. So from a designer perspective, we always try to keep these values low here. So now we are going to share a few of the examples here based on this UWB inspired antenna design here, which we proposed here. This could be possible, could be utilized with the IoT devices here in the future. And then last, we will see one of the demo once we deployed the antenna near to the bodies here. Then what kinds of results we have observed here and what are the problem we have faced here, we will share with you those experience here. So this is the antenna part here. So this is the one example we have used the coarse fractal antennas here in this part along with not only on the generator part here or you can say patch part here, we have also introduced in the ground part too here. So this help us in the enhancement in the overall bandwidth of the structures too here. So this work is totally based on the fractal geometries and their property utilization. So here you can see how the iteration wise we have evolved the antenna as well. So when you are looking for the evolution of the antennas here, fractal geometry here, we have generally considered the hexagonal or octagonal kind of shape of the structure here. The reason is because we need some arm here where we could deploy or apply such kinds of coarse properties here in the design. Another advantage was when I'm going to use such kinds of design or after the iteration, these structure is highly likely have some similar in nature like the your circular structures here. So I will have the circular structure kinds of structure here after the iteration here. So wideband phenomena will be present here as well as the fractal I already applied. So the self-similar and multiple resonances will be present here. So they will further enhance the isolation part, S parameter part here within the band here. So this way it will facilitate us in the operating the wideband phenomena here. So this is the surface kind distribution we can observe. And one more thing in the my first talk here I emphasize whenever you put the bands and other things here, at that time it will help in the enhancement of the radiation here. So you can observe corresponding to the different structure here when I am placing here, this kinds of deformation in the design through the fractal I am substituting here at all those bands and curves here. You can say the surface kind of distribution intensity is high. So all these factors and curves are enhancing in the surface kind distribution here or in dense surface current will help us in the enhancement in the radiation here. That's why we get the advantage here. Similar, these are the impedance properties of the structure here, and these are the S parameters here. These are the radiation parameters related to the antennas part here. We have seen these are the measurement of the antennas. These are the time domain analysis because when you go for the UWB antennas here, so time domain analysis is very important aspects here because within the band, based on the antennas shape here, how it is affecting your transmission characteristic here. So to measure those things here, we need to go for the time domain analysis here. So it has utilized the fidelity factors here. So in this part, you need to simply place the probe here in the surrounding with the antenna, collect those powers here, and then you go for the cross correlation matching. You could find out what will be the fidelity values here. So if it is close to 1 here, then it is very good. If it is values keep on decreasing, means the deformation will be keep on increasing here. So in the 360-degree complete plane here, we have tried to observe what is the value of fidelity factor is present here. This is another design where we have using the Minkowski geometries here to explore the fractal advancement here. This is another one where you use the Sierpinski here. Not Sierpinski. This is again the Minkowski here, but a different perspective here. So here, if you can say kind of dipole kind of structure we have utilized, and here we are used on the octagonal shape here. There is another structure where we are using the Sierpinski here. I think someone speaker is unmuted here, so if you could unmute it, then it will be good for all of us here. So there are another antennas where they have used Sierpinski fractal geometries here in the design. Here, and based on that, they have observed the UWB. And this is another work here which have been explored further for the UWB antenna part. We have taken it further for the MIMO level here, and still the other S parameter surface current results here. The other S parameter results here with stub, without stub, and these are the different analysis related to the same structure in the fabrication, then simulation and measurement results here we have observed. This is also some other radiation related results, gain, capacity loss, ECC, related to the antennas observed here. Then UWB reconfigurable antenna related to the bandwidth reconfigurability here. So these kinds of work will be more appropriate for the IoT applications here, where you can use them here, where we can have the functionality to switch from one band to the another band also here. If there is a specific interference in some of the band here, where you use the band notch to what how it affect the significantly here. So to explore these aspects here, so we have the simulation environment we have done, as well in the measurement aspects we also explored this work here. So the one antenna we have discussed thoroughly in the starting here, the same antenna we have considered network aspects here. So we design layered human body tissue model here, so where we have considered different thicknesses based on available in the literature here. We directly taken values here, because if you go through the literature here, you will find there is a term called the Cole equation which is present here. So based on that Cole equations here, you can find out within the different bands what need to be the operating dielectric values, loss tangent here, as well as thickness of those things. Those parameter information given the inspiration from that and design this body tissue model here. So based on the different layered thickness of skin, fat, muscle, and bone here, we have tried to replicate it, and then we have put the antennas on top of it here and investigated the characteristic of the antennas here. So here, this was the measurement model here, simulation we have done, as well as the measurement part we also done here. So measurement part, there was a horn antenna we have put in the anechoic chambers. So it was connected to the VNA. So one VNA was giving the power to the horn to the one port, and the port was connected with the antenna itself here. So we are transmitting the power to the horn here, and the person which was present here, we have placed the antenna at the different level and try to find out what were the observations here. So on model d is equal to 0, d is equal to 5, and d is equal to 10 meters. So this distance we have varied once we put the antenna directly on the body, and then we have put a difference of 5 mm and 10 mm here, and then we have measured the results values here. So you can observe here, so when I am substituting, putting the antennas at the body part here, so it is affecting significantly here, correct? So this is a significant change. It is observed here when I'm putting the antennas at the different location of the body part here. This is the further placing of the antennas here. In that case, we have put three places. One was abdomen, another is near to the forehead here, another was chest here. So one is near to the forehead here for EEG signals, then ECG signals here, and the abdomen signals here. So for these kind of signals, we have placed it here, and then based on that different distance, d is equal to 0, d5, and d is 10, three cases we have investigated and find out these performance here. These are the radiation performance of the antennas. It is distorted, but still it is okay. For W-band applications too here, we have explored, in this case, the MIMO antenna. Previous case, we have used a single antenna system here. Now we have moved one step further here. Now we have tested the 2x2 MIMO antennas here in case of body air network application here. So similarly, similar way, we have put the antenna near to the abdomen, chest, and the near to the forehead here to gather the signals here, and based on that, we have observed how it is affecting the significance here. These are the radiation performance related to that, and these are the few SAR values which you also calculated here to the simulation environment here. So, based on that, now we could conclude what could be the possible research problems here based on our investigation here. So we could say the other fractal geometry could also be possible applications, or other component of the communication system like filters could also be explored, or oscillators and other things could also be explored here with the other fractal geometry, as well as for the other possible applications here. And the other from the more precisely in the context of wearable technology, if you see, to avoid the RF losses, integration of transceiver on patch antennas here. The complete chip here can be put it here at the antenna system. So as we are moving to the higher frequency, these possibility would be arises here to integrate everything and put a one chip here, which will be having all the desired component from sensing the information to the communication of that information, having all those aspects of communication here. Combining several patch antennas here, as we have seen one case here, so the MIMO here, as we have seen, the deformation was significant here. So can we go for a more sophisticated solutions here, where we could club the power more efficiently here, and we have the liberty to go for the design of front and back antennas, because in this case we are going to use the antennas only one radiator part here only here, and as well as the polarization, because once I am going to use the antenna on the body area part here, if it is circular polarized here, then it is much more useful to us here compared to the linear polarization here. Linear polarization is also used here if we know this is the my direction of transmission, where I need to transmit here. But when you say the circular polarization, it doesn't mean it need to transmit the power towards the body here, but what is coming outside within that plane, it need to be directions here. So circular here. These are a few of the references. Okay, thank you. That's all. Now the session is open for a question and answer. So if you have any question, you may ask, please. So I can see there is no question from the chat box. Any question? So related to the body network part here, if you have any doubt, whatever we have discussed in this session here, you can ask here. I think all the participants have left for their lunch. I am the only one as a speaker.
Sir, what should be the gain of this variable antenna, because it is close to body?
Yes. So when you talk about the gain here, based on the compactness here, still it is 2 to 3 dBA gain we can obtain here. But a few of the papers I have seen, they have proposed here that they are able to obtain 5 to 6 dBi gain here.
So whether large gain will be beneficial, or it will be drawback, because it is close to body.
Yes, as we are considering based on the application, you need to take a call here, because if I am talking for the narrowband applications here, the narrowband application getting the gain is relatively easy. If I am talking about the wideband antennas here, then the same gain level will be achieving will be very difficult here. Correct. but within the same lower gain also, with the enormous amount of bandwidth, you can have the more channel capacity compared to that here, because the SNR will value will compensate even with the lower gain value also here. But overall, you can say whatever the spectrum are asking here. So gain is always a good here parameter. But when you're looking for the body and network perspective here, then at that time you need to be very critical in terms of its directional behavior, in which direction antenna is transmitting. It is just like when I'm using the phone here, for the mobile phone I'm tracking here. If I'm using like this in this orientation, so one beam is already coming from here to the my head side here. It is present here. I cannot nullify this beam here, correct? Because if I nullify this beam here, then I will not be able to listen anything from this mobile phone here. So I have to keep that beam level present towards the head side of the here. But similar way, when I am putting some sensors here near to the body here, I have to be careful in terms of this radiation beam of that sensor here or that device here, so that it one need to sense the information here. Sensing purpose, I need to provide some beam here, but it should not be very narrow or very penetrative here. As we observed in case of high frequency here, when you go high frequency, this beam is going to be narrow here. So I need to be careful at those points here, because if it is very narrow here, if I provide the more power here, it will penetrate larger distance here. So if it is sensor perspective also here, so I need to be careful in terms of directional behavior, because one need to be near to the body type also here, but it should not be too much, so that it could harm our body here also. So you can understood think of if correlated with the functioning mobile phone behavior here, and if you try to correlate with the sensors which we are trying to deploy on our body part here, so you will find a correlation here. You can take input from there also, motivation for also the design. Okay, did I answer or still I missed something?
No, sir. Perfect.
Okay, so any other question? Is there any major problem with UWB antenna? Okay. So one question is UWB antenna. So when you talk about the UWB antenna perspective here, then there is a limitation in terms of range of communication here. So this is the limitation, because we are transmitting at a very low power level here. So I need to be careful in terms of its power related to the power here. What would be the range of transmission? Because as its power is already substantially decreased compared to the other technologies here. So with the distance traveling here, it will be keep on decreasing further here. So I will not have the liberty to go for a very long distance communication with the help of UWB technology. The UWB technology is especially intended for such kinds of body and network application, especially wireless body and network applications here. We can use it. So this is the limitation here, but it is not the problem. It is the limitation with respect to the technology itself at the stage where you have designed here. Okay. So there's no further question in the chat box. So if anyone have more, you can ask me. Okay. So I think Unni MR. So he is. So no further question. Okay. So I think with this note here, as there is no further question from your sides here, so I'm taking a liberty to close this technical session here. So this is the last technical session from this FDP. So next session we will meet Mr. Nitin Srivastav. He is a very good meditation and yoga teacher here, and he will give a talk on the stress management meditation and yoga.
Sir,
So
good afternoon, sir.
I request Unni MR to please unmute yourself here.
Good afternoon, sir. This is Rajeshwar from Chandrapur. Hello, Shrivishal, sir. Hello, can you hear me, sir?
I think I unmuted myself. I unmuted myself here. So you were saying something, Lakshmi Nayan?
Sir, presentation.
Okay. Presentation.
We are going to
Okay.
share the presentations.
Okay, I will club all the presentation from other speakers too here, which is available with me here. So after that, after the next 1 or 2 days, I will send the link with all of you here. Those who are attending.
Okay, sir. Okay. Thank you, thank you, thank you, sir.
Yeah.
Okay.
So next session here it will be stress management. So meditation here. 2:30 we will start. And he is a very good speaker here, and the past he was associated with the triple IT in few of the activities. So he is very good in those aspects here. So you all will be benefited from that sessions too here. And during that session here, we will start collecting the feedback from the our side. So one will be communicated, and other you need to also complete it at the AICTA websites too here. So that part you need to take care, because if it is not here, then e-certificate will not be generated. So that is the mandatory condition of AICT here. Okay. So with this note here, I am closing this technical session of morning session here, and we will meet again at 2:30 p.m. and after the lunch here. Thank you. Thank you very much.